Today, we're diving into a seriously revolutionary piece of tech, a silicon chip that you program not with electricity, but with light. This is a huge shift in how we even think about computer hardware. You know, for decades, all our computing has run on electrons zipping through circuits. But honestly, we're hitting a wall. We're running into bottlenecks with speed and efficiency. So the big question is, what if we could just swap out those electrons for photons, particles of light? They're way faster and they generate a whole lot less heat. Okay, but this is where it gets really mind-bending. What if this light-based chip could actually program itself? Yeah, this image you're seeing isn't just some abstract diagram. It's the blueprint for a device that can figure out its own best-case scenario configuration, and get this, even heal itself if a part of it breaks. All right, so how on earth does something like this actually work? To really get it, we've got to peel back the layers, kind of like an onion. We're going to start with the big picture and zoom all the way down to the one tiny component that makes it all possible. So at the highest level, what you're looking at is a programmable photonic circuit. A good way to think about it is like an FPGA, a field programmable gate array. But this one is built for light. It's this complex mesh of tiny, tiny channels called waveguides, all etched right onto a silicon chip. The whole point is that it can be reconfigured on the fly to do a ton of different jobs. Now, this whole structure isn't just a random jumble. If we zoom in, you start to see it's built from these repeating hexagonal modules. They're called unit cells. Each one of these cells is like its own little self-contained processing block, and when you link them all together, well, that's where the real power of the circuit comes from. Let's zoom in one more time. Right at the very heart of every single one of those unit cells, we find this little guy, the Tunable Basic Unit, or TBU for short. It might not look like much, but this is the fundamental building block. This is the tiny programmable switch that gives the entire chip all of its power. So, we found our core component, the TBU. But what does it actually do? Well, it all comes down to a really, really clever way of building a switch that can control the flow of light. So the technical name for a TBU is a Mach-Zehnder interferometer. It sounds complicated, I know, but the idea is actually pretty simple. It's a circuit with two couplers that can split a beam of light and then bring it back together. And right on those central arms, you've got what are called thermal phase shifters, which are basically just tiny, incredibly precise heaters. And how it works is based on this beautiful principle in physics: interference. Here's the play-by-play. First, a light signal comes in and gets split perfectly into two paths. Then, we apply a little voltage to one of those heaters. This gently warms up the path, which actually changes the speed or the phase of the light going through it. When the two beams of light meet back up, they interfere with each other. By precisely controlling that tiny difference in phase, we can dictate exactly where the light exits. It's brilliant. This precise control gives us three basic programmable states. If you apply 0 volts, you get the cross state, where light just crosses over diagonally. If you turn the voltage up to around 2.7 volts, you get the bar state, where the light passes straight through. And somewhere in between those voltages, it acts as a tunable coupler, splitting the light perfectly in half. Now, here's the crucial part. With just those three simple functions, cross, bar, and split, you can build almost any optical circuit you can possibly imagine. Okay, so we have our Lego bricks, these tiny programmable light switches. Now let's see what happens when we actually start snapping them together to build some real functional circuits. So for their first application, the researchers programmed a specific arrangement of these TBUs to create an optical filter. What they basically did was build a much bigger version of that Mach-Zehnder interferometer we just looked at, creating two separate paths for the light that had different lengths. And the results are crystal clear. The graph shows that classic wavy pattern, those peaks and valleys that are the dead giveaway signature of interference. This is the proof. It confirms the circuit is successfully filtering out specific wavelengths of light, behaving exactly as it was designed to. But here's what's so powerful. Using the exact same physical chip, just by sending it a different set of voltages, the researchers created a completely new device. This time, they programmed the TBUs to form a closed loop. This creates a structure that can actually trap light and make it circulate. It's called an optical ring resonator. And once again, the results just speak for themselves. These incredibly sharp dips you see in the graph are resonance peaks. That's the undeniable sign that the circuit is acting as a high-quality ring resonator. And this is a huge deal for things like telecommunications and advanced sensors. So just think about that. Two completely different devices from one single piece of hardware.
Look, building circuits with light is already a massive step forward, but this technology has another capability that is, frankly, a total game changer. Let's talk about the chip's ability to program and optimize itself.
This is what's known as self-configuration. It's the chip's ability to automatically check on its own components, find the best possible path for the light to take, and tune itself to hit a specific goal. It uses clever algorithms and feedback loops to manage the incredible complexity of controlling thousands of these individual TBUs at the same time. Now, the researchers showed two main ways of doing this. You can think of it as the map versus the explorer. The first method, pre-characterization, is kind of like creating a perfect, detailed map of the entire chip first. Once that map exists, programming a new circuit is incredibly fast. The second method, computational optimization, acts more like an explorer. It treats the chip as a black box and uses algorithms to just try different settings over and over again until it finds the best one. It's a bit slower to start, but it's way more robust and adaptable. And this explorer approach is where things get really powerful. The researchers simulated what would happen if 3 of the TBUs were completely broken. Well, the algorithm didn't fail. It simply found an alternative route for the light, programming a different set of TBUs to get the exact same job done. This is, for all intents and purposes, a self-healing circuit. So let's just step back. We have a chip that is programmable, multi-purpose, and even self-healing. This is not just some academic curiosity. Let's talk about the massive potential this has for both research and the business world. As traditional silicon chips start to really bump up against the physical limits of Moore's law, this kind of technology could open the door to the next generation of hardware. We're talking about the backbone for future 5G and 6G telecom, specialized processors for AI and deep learning, and even some of the foundational components for quantum information systems. It promises faster data centers, more sophisticated sensors. Really, it's hardware acceleration at the speed of light. And you don't have to just take my word for it. The researchers who developed this tech put it best themselves. They said, programmable integrated photonic circuits have been called upon to lead a new revolution in information systems. I mean, that's a pretty powerful statement. So, as the age of electronics starts to face some very real, fundamental physical limits, the question we have to ask is this: could self-programming photonics be the technology that defines our next great leap forward?